right, hey everybody. We're back. This is start unit 4, and we're talking all about waves. So this whole unit is going to be talking about um, oscillations of sort. And the main focus will be on sound. So we're going to start off talking about introducing the ideas of wave, how to quantify waves, talk about frequency, wavelength, all those terms, try to get a general sense of waves and sinusoidal motion. You guess what sinusoid? Talk about that. Or another way you can think of it is what we call simple harmonic oscillators. Think back and forth. The best examples of it is sound, and we're going to talk about how sound interacts, have constructive and destructive interference of sounds, resonance, and we're actually going to try to build musical instruments. Okay, that's our main thing we're going to get in this unit. Oh, I did my. Okay, all right. Sorry. So let's. All I want you to do this lesson here, is go on the Weebly, okay, and instead of me going through all this stuff, I have a list here. There's a worksheet with a whole bunch of terms. For us to actually to talk about waves, we need to figure out a whole bunch of different new words. So I want you to go through the sheet and by yourself right now, stop the video and find it all. So please stop the video right now. Pause. I'm waiting. Pause the video, okay? And go through all those definitions. I'm going to wait and start the video up again, and we're going to go through the definitions together. If you like my definition better than yours, then use that one. If not, stick with one you have, okay? So, see you in a bit. All right, so what are some of these definitions? First one, wave. What the heck is a wave? It's a very simple question when you think about, what's a wave on a beach, but what's a wave in a more general physics sense? So, in our understanding of waves, a wave is merely an oscillation. Okay, it's back and forth. Oscillation that goes in one direction and then back the other way, and keeps going for some reasons. Restorative force pulling it back and forth, and it goes through some sort of a medium, something that wave travels in, whether it's a water wave, water molecules go back and forth, or sound, they use air molecules back and forth, or in something really complicated like light, where it uses itself as the medium, where it uses interaction between electric fields and magnetic fields to sort of oscillate itself. That's really complicated, and we'll talk about that in grade 12. But know that just for now, a wave is something that goes back and forth. And this idea of going back and forth can also call periodic motion, in that motion repeats itself. That there's some sort of repetitive thing. It could be as simple as going back and forth, or there could be a 1, 2, 3, 1, 2, 3, some sort of repetitive action that happens. All right, it could be a seesaw wave, or it could be any sort of thing that has, after a certain period of time, the motion repeats. So there's a period. This time that it takes for the motion to repeat, we call a period. Transverse vibrations. So this is when we have a wave traveling in some direction, and the oscillations are perpendicular. That's the important piece in this. That the vibrations, the oscillation, the direction in which things are vibrating, are in the opposite way of perpendicular to the propagation. So, for example, a guitar string, let's say, or any sort of string, sort of material under some sort of tension. If I sent a wave down it, it's going to travel in this direction. So this little hump will travel along that material. So the wave is traveling in the material, and the oscillation is at right angles, that motion. That's what we mean by that. That's a transverse wave, like a guitar string. Have transverse waves. The amplitude, or the direction in which we are so the disturbance is perpendicular to the propagation of the wave, as opposed to what we call the next one, which is longitudinal, where the oscillations or the displacements are in the same direction. So in sound, for example, we have compression, and sound is just air. All our air molecules are compressing and stretching. So our wave is traveling like this. Like that. Okay, so I have my air molecule. I have a little bit of air, and then a speaker, let's say something, or my vocal cords, pushes it, and it squeezes this air a little bit. That pushes the next one over, going back and forth. This wave is propagating in the air, it's traveling in this direction, and it's squishing, or the amplitude, or the way in which it wobbles back and forth, is parallel. It's in the same direction as propagation. Okay, so longitudinal is like this. The wave is going in up and down, whereas the wave travels from, what's that, left to right for you guys? Not sure. And it goes up and down. Whereas in longitudinal, it's going with it. So that's the difference, transverse and longitudinal. One cycle is defined as one full oscillation. So when our periodic motion goes through a full oscillation, full up and down, or whatever pattern happens there, whenever it returns back to the original state and starts over, that's one cycle. You can think about it like in on a swing. If I start in the middle, and then I go up, and I come back, and then back. When I get back to the middle, that's one full cycle. Okay. So I've gone from my origin, my equilibrium point. I've traveled in one direction. I come back, forth. So once I've returned back to my original state, that's one full cycle. Or if I'm measuring from the other side, I have to go my full extension in the other direction, back. Okay, that would be one full cycle. Frequency. Frequency then measures how many of those cycles are in 1 second. Okay, so for example, sound, or we can hear anything between our ears are tuned from 20 hertz, that's 20 cycles, all the way to 20,000 cycles, hertz. So that means like typically an A note you play on a piano is 440 hertz. Okay, so that tells me that in 1 second the air is vibrating back and forth 440 times. It's the frequency of the vibration of the air. Right, it would be the same as the frequency of the vibration of a guitar string. The guitar string, say, going up, down, and back again. So one full cycle, up and down, and then back again, 440 times a second. And that's pushing the air. That's causing that 440 hertz, that 440 cycles a second. Okay. Hertz. Sorry, I kind of got ahead of myself there. So hertz is what we use to measure our frequency. It's 1 hertz is defined as 1 divided by a second. It's how many cycles happen in 1 second. Okay, frequency is number of times so that's the frequency defines the number of times it happens in 1 second. We measure it in hertz. Whereas the period is the time it takes. This one we use a big capital T to define our period. Frequency is a little f. Okay, the period is the time it takes for one oscillation. Okay, one cycle can be measured in time as having a period capital T. And you can see here that the frequency then is going to have to be 1 divided by the period, which is how you can see units of seconds. Right? So the time it takes for one full cycle, called the period, and the number of cycles in 1 second is the frequency. Amplitude tells us how strong it is. So very quiet. But if I'm talking very loudly, everything's moving a lot. That's a large amplitude. Or on a swing, when if I'm just swinging back and forth a small amount from my equilibrium position, that is a small amplitude. But if I really go, right, and that has a large, capital A, amplitude. Okay, that's amplitude measures the amount at which an oscillation goes. Phase. Okay, so phase is kind of tricky here. When I have two different waves, say I have, there's my time axis here, that kind of, and I have one wave up and down like this. If I have a second wave also happening at the exact same time, they're going to build up on each other and louder. If it was sound, it'd be louder. Okay, so when they line up, when the two waves have peaks and troughs at the same time, that's called in phase. Whereas if it's out of phase, that would be when we have one wave that goes up and the other wave goes down. If I have one amplitude going in the opposite direction, one amplitude in the negative direction, they're going to cancel each other out. Okay, when they're out of phase, we actually have no sound happening. Or some of the sound isn't happening. That's why you have to make sure when you plug in your speakers, you get the wires in the right direction, or else your speakers will be out of phase and they'll sound funny. You'll have dead zones. Talk about that later when pictures of these. Okay, but just quickly, in phase means that they're lining up. Out of phase means that they cancel each other out. They're in opposite directions of each other. Another way you can think about it is there's a translation of 180 degrees. Call it a phase shift of 180 degrees. That's a Greek, so that's a delta. You can use a delta, or if you want to be super fancy, you can use a little Greek f for your phase shift. This is a lowercase Greek f, phi. Okay. All right. Transverse wave. We talked about that. Look. Where was it? Transverse vibrations. Where was that? Over here. When the oscillations are perpendicular to the propagation. Crest. So that's the largest point. That's the maximum of our wave. Whoop. The crest. Maximum oscillation, and the minimum. Do this. This would be the trough. Peak and the trough. Periodic waves. This is when waves repeat after a certain period. So they have a period, some sort of oscillation that repeats, and they have waves. Waves can be determined in a sort of more mathematical way, which we'll talk about. So let's not worry about that now. Leave it at that. Wavelength is quite easily defined as the distance between those maximums. Let's say I have a wave here and it keeps going. My wavelength, now this is a funny letter, this is the Greek letter L, or a lambda. Lambda. Okay, and that defines the distance between crests, or alternatively, the distance between troughs. Or you can also do it from one equilibrium position to the second equilibrium position. That's also a lambda. All of those are the same length. They're all the same. It's the amount of distance that has to happen for there to be another wave starting. Okay, so it's like a position variation of period. Period tells us how long it takes before another oscillation happens. Wavelength tells us how far before another oscillation happens. Okay, and this is measured in meters because it's a distance. Wave front. This is a little bit tricky. We add up a bunch of waves. They make a surface. We call that a wave front. Think about it like when you're on the beach. All the little waves that are produced out in the ocean from a bunch of wind all build up, and eventually we get to the beach. Here's the beach. As a whole, if I'm looking from above, a whole line of these waves coming in, these rollers in to the beach. This whole line of waves we call a wave front. And then the wave ray is then a line going in a perpendicular direction to the. So when there are lines like this, we call that a wave front. Or if they're all coming out from, let's say, some sort of a point source, all of these lines themselves are their own wave front. We'll talk about this when we look at what we call Huygens principle, how waves actually propagate. And then again, we'll have a wave. So the wave ray is a line perpendicular to the wave, and the wave front is sort of the line of the wave as it travels. A little bit complicated. We'll talk about it more later. Refraction, you've seen before in grade 10 optics when we saw light bend and it changed from a different medium. So, for example, I think you guys should have seen this. It's called Snell's law. Snell's law, when light hits a medium, so here's normal to the medium, comes along, it's going from air, let's say, it hits water, and it bends. This is because the light actually slows down. We did this in grade 10 again, that the speed of light in a material was the regular speed of light divided by n, which is optical density, or the index of refraction. So this changed, as the light slowed down, it had to bend necessarily to keep the waves lined up right. We call this refraction. Another new word, though, is going to be diffraction. You know that if there's a door open and there's people outside, you can hear them. How is it possible that the sound is actually, you don't have any line of sight with the source, but you can still hear it? How is that possible? It's because sound or waves are able to diffract. They're able to, let's say here's the door, and there I have these wave fronts all coming in and hitting the door. Are they, as they go through, are they only going to be traveling that? No, they're going to bend. They're going to, what we call diffract around. It's going to be diminished. The amplitudes are going to go down, but there's going to be this stuff here is called diffraction. The sound or light can also diffract if the aperture is small enough. Aperture just means hole. So this is my hole here, my material. This is the wall. There's the door. Okay, the sound's coming towards it, and it doesn't just go through. There's also all of this stuff which we call diffraction, bending. So refraction is when it hits a new medium of the different density, and it has to change speed, so then it bends. Diffraction is when it bends around an aperture. Instead of just traveling right through, let's say if I throw a ball, there's no way that the ball is going to bend, right? A material, some corpuscular thing is unable to somehow magically go to left or right. The only way it can do that if it's a wave, because the wave then will take the material at this point and will start producing more of them, more waves, and it will diffract around it. It's how you can hear sound a doorway when you can't see the person talking. So refraction is it bending from changing material. Diffraction is when it goes through a hole and is able to go around it. Speaking of which, interference. This is when waves are building on top of each other or cancel out. We can have constructive or destructive interference. We'll talk about a lot later. And resonance. This is a wonderful property of waves. You've all seen this. What do I have here? When an oscillator is forced at the same frequency as its natural frequency, leads to a dramatic increase in amplitude. You've all seen this. Ball swung on a swing. How do you swing on a swing? Right? If I get somebody to push me, I'm just going to eventually stop. How do I keep going? The way you do that is you move back and forth. You move your legs at the right frequency, the same frequency as you want the swing. Wants to swing at. Okay, this is called resonance. You're forcing a system that has a natural frequency. Anything that has some sort of simple harmonic motion like this has a natural frequency that it wants to vibrate at. If I'm forcing it at the same frequency it wants to vibrate at, the amplitude increases dramatically. All that resonance. And it resonates. When you're on a swing and you keep moving your legs back and forth at the right frequency, if you move your legs back and forth really quick, you're just going to wiggle there. If you move them really slow, nothing's going to happen. But if you move them at the right frequency, the correct frequency which it naturally wants to vibrate at, you're going to start swinging. Okay? So that's called resonance. Talk about that a whole bunch. Very important concept. Waves. Oh, and there we go. All done. Okay, so hopefully you've gone through all those sheets and you got them all done, and we'll be seeing you in the next lesson. Take care.